all the controls, but still Google Meet is improving day by day. Like at least it's free till now. They are not charging us.
Yeah, no, I
So in
think
future we don't know.
they should have an option where I could see the participants while presenting, because otherwise
Yes.
it just looks like I'm talking to myself. So,
Hello, sir.
hey Satya, how are you?
Yeah,
I am good, sir.
Good, good.
Yes, sir.
Thank you for inviting me, Satya.
Thank you, sir. Thank you for accepting our invitation.
so Satya is our future chair actually.
Oh, really?
For our next student branch.
He's invited me.
Yeah.
He's invited
So
me before even becoming the chair. He's doing the job of the chair.
So,
Thank you, sir.
so after I guess 3 or 4 minutes we'll start.
Okay.
So, right now we have 23 participants. So from our previous analysis, we have approximately 50 to 70 participants on average. Actually.
Oh, really? Okay.
So online is that the good thing actually, like because here only we have our chapter students or volunteers attending, but for online, like we have a good social media platform, and then from there we could circulate and like used to get a lot of participants. In IIT Kanpur, there is one more talk of yours, I guess, on chip antenna.
Yeah. I'm giving this week in IIT Kanpur. The following week I am giving in IEEE workshop in Dubai, and the following week I am giving in one talk in Sydney. Actually, 2 talks in Sydney in ISAP and in the chapters. The last week I gave in Milan, in Italy. So this is just a heavy month for talks.
Yes.
So just let me know when I need to start, okay?
Yes. So right now we have around 26 participants.
Yeah, and the time has just, it's just 4 p.m. It's like the right time now.
Yes.
Maybe give a couple of more minutes to people to join in?
Yes. Just couple of more minutes. I'm just taking out few things.
No worries. No problem with me.
I guess we can start because we have this short introduction and then the formalities.
Okay.
So yes, so with your permission, we could start, I guess.
Sure.
Yeah. So good evening, good afternoon Good morning, wherever you all are. So this is our series of talks. So this is the second distinguished lecture talk that IEEE AP-MTTS IIT Kharagpur is being organizing, and we are really glad to have Professor Atif Samim. So just recently I have met him. I was lucky enough to meet him physically during this European Microwave Conference in Milan. It was really great meeting him. Although Professor Atif Samim is known by the field of on-chip antenna, but he will be giving a different talk here. So, and he is a man. So I will be just giving a short introduction of Professor, and then we can start. So Professor Atif Samim has received his both MS and PhD degrees in electrical engineering from Carleton University, Canada in 2004 and 2009, respectively. He was a NSERC Alexander Graham Bell Graduate Scholar at the Carleton University from 2007 till 2009, and an NSERC postdoc fellow in 2009 to 2010 at Royal Military College, Canada, and KAUST. Recently, he is a professor at KAUST, where he is a full professor and also a principal investigator at Impact Lab. He is a receiver of many awards, a person who we all know. We also know him as the father figure of on-chip antennas. Recently, he has also shared his stories on on-chip antennas. So without any further ado, we would welcome Professor Atif Samim to share his valuable knowledge with among our community once again. So Professor, to you.
Thank you so much for the kind invitation, and thank you so much for a nice introduction. Though I like the father figure of on-chip antennas, is very flattering, but actually I'm not there. There are many people senior to me who have been in this field before me. We have done a little bit of our part. And by the way, people who are interested in the on-chip antenna work, I'm giving a talk on Thursday to IIT Kanpur, and I think that's also an online talk. So the people who are interested in that talk, they can join that talk as well. Here I'm doing a different topic. My lab does a lot of printed electronics, so I'm gonna show you that. So let me just share my screen with you guys. So can you guys see my screen now?
Yes. And you can start. And also a couple of bookkeeping stuff, like we could go ahead at the questions at the end. So you could keep your questions and then at the last we can discuss. And I guess that would be great.
You can keep on putting your questions in the chat window, and we can go back to them towards the end of the talk, okay?
Yeah, that would be also fine. Great.
Okay, so let me start. As you know, in the introduction, my training is in CMOS RFIC design. So that's my PhD was when I was doing IC design for biomedical sensors. But then since I'm in KAUST, you know, I've got into this printed electronics a lot, and I like to do low cost, flexible, wearable, low cost, disposable kind of electronics. You know, so today I'm going to show you some of that work which we have done over the period of years. So look, the wireless journey really in 1973, I think it's just almost 50 years. Now, the first call when Martin Cooper, walking in the streets of New York, he made from a mobile phone, right? And this call was, of course, he's from Motorola. So, and there was a competition going on to have the first mobile phone, and people were working on car phones at that point of time. And you know, the first call he made was to his competitor in Bell Labs, and he just said one line that I'm calling from a mobile phone while walking on the streets, right? So this was a big step forward. But if you now go 50 years later, we have like more than 7 billion mobile users, right, across the world. This is such a big invention. And not only the wireless phones, mobile phones, but, a number of wireless technologies are part and parcel of our life. Wi-Fi, GPS, Bluetooth, we all use it on a day-to-day basis. So wireless has really become part of our lives. Now, but people like us, who are researching in this area, we look at what's coming next, and what are the challenges, which we are going to go forward. So if you look at some of the big applications, which are 6G, of course, we are looking forward. 5G is already being installed. 6G, people are moving towards 6G. Internet of Things, IoT, a big paradigm shift, I would say, where non-living things start to make decisions for humans. So you need billions and billions of wireless sensing and wireless communication devices. Then, of course, connected cars, autonomous cars, connected cars with the environment's vehicle to everything kind of communication. So this is a big wireless application. And, of course, augmented reality or virtual reality. These are kind of the big applications for having the next wave of the wireless. So what do these applications or what do moving forward demands, this means we have to move on higher frequencies. 6Gs, we're already talking about close to 100 gigahertz or above, or 140 gigahertz. And there's, of course, you need compact size, you need higher level of integration. You need, if you want to do billions of devices, you need lower cost. We are always looking for lightweight and conformal, kind of designs, and with enhanced functionalities, right? So look at what your phone can do now. All the functions are built in, but we need more and more functionalities in a lighter weight, low cost conformal platforms. So these are the kind of challenges which we take up in my lab. Some of them actually are covered by the on-chip antenna stream, and some of them through the printed electronics. So here are the areas, which three areas where we work in our lab. One on the top is the system on chip, the RF system on chip, where we do IC design, where we integrate circuits with the antennas, and this interface, especially this interface of circuits and antennas, is very important to us, and we have done a number of things, and that's the talk I'm going to give on Thursday in IIT Kanpur. Then we also do a lot of work on antenna on package, where the package is made functional. Typically the package of electronics is a mere cover; it just protects you from the environment, but we want to make this package functional. So we have done like complete millimeter wave phased arrays in a package. Made the package like a lens and stuff like that. So all the electronics is embedded inside, and the antenna is on the package. So this concept is also picking up, and I know companies like Sony Ericsson and all those, they are now trying these in their mobile phones. But we're not going to talk about this today as well. Today what we're going to talk about is the printed electronics aspect, right? Where we could print electronics, hopefully one day, like newspaper and magazines. And we do a lot of communication and sensing, whether it's environmental sensing, whether it's biomedical sensing, and we're going to talk about that today. Okay, so printed electronics is picking up, especially for applications like Internet of Things. Now, if non-living things need to make decisions for humans, you need to have a lot of sensors, and you need to have a lot of communication. And these wireless communication or wireless sensing devices need to be placed on different shapes, a car, a home, even on humans. So they have to be mechanically flexible or conformal, right? So look at this. This is a company I met in California, Temtrack. They have this sticker kind of a Bluetooth temperature sensor, which is flexible. You could put it on a child, and the temperature keeps on coming to the parent's phone. Imagine there's a hard PCB, rigid PCB. Can you put it on a child's body? No. So there are a number of applications, and trust me, the automotive industry, there are already printed electronics components, which are like HVAC system, for example, are already there, right? So there are a number of examples of printed electronics which is coming up. So, because this is an RF microwave or antennas chapter, and maybe people are not familiar with the printing, so I thought I would give a little bit of small tutorial in the beginning before going on to the designs and the applications. So we call it additive manufacturing, and you will find out why. Because this is the typical traditional manufacturing which we do right now, which is called subtractive manufacturing. Even if you take a printed circuit board, it has metallization on both sides, right? So if you want to create your layout, let's say if you want to do an antenna, what you do is that you create a mask or create a screen, and you etch the material, etch the metal to create your layout. And this is what you are removing or subtracting material, right? And that material is wasted. So same thing happens in the clean rooms. You do a blanket kind of complete material, then you do masks, and then you do lift offs and etching, dry etching, wet etching, and you remove them. This is how traditional electronics manufacturing is right now, which is called subtractive, right? So of course there is material wastage, there is expensive masks, there is clean room processes. Printing, on the other hand, or additive manufacturing is just like printing in your home and office environment. If you have the right ink and printer, you could make your layout only on a host substrate for the structure which you want. You do not need a blanket material and then etch it, then remove it. You just add material where it is required. Like when you print in your home and office environment, let's say you're printing a diagram on the paper where you print, only that diagram appears, right? So the material is deposited only where it is supposed to be and not everywhere. So this is very, very good for low cost and large area electronic systems like RFIDs, IoT, as I said, solars. There are a number of fields where they're being used, and they're nanoparticle-based inks which have really improved the conductivities, especially talking about the conductive inks like the metallic inks, and that's why this is now becoming a reality. Also, there are now new functional inks. I'm going to show you some of them, which can basically enable low-cost sensing. And you could print on pretty much any substrate, right? You're not restricted to a PCB. Plastic, I'll show you, we have done print on unconventional substrates. And eventual goal for people like me and people like me who are working in this area is that to be able to print electronics like newspapers and magazines, like roll to roll, like big rolls going on and printing with high speed. So imagine how many millimeters wave scale or micrometer scale devices can you print in 1 minute, millions, right? So that's the kind of throughput we are talking about. And this is what is known as additive manufacturing now. So whether it's screen printing, it's inkjet printing, it's 3D printing, different forms of printing, but they're all additive manufacturing. Okay, so let me give you an example of how we make the inks and how, and because there are some important parameters which you need to understand. First of all, we want to make the nanoparticle. Let's say if we are trying to make a conductive ink, a metallic ink, we take the metal salt, the form of salt, and then we add some reducing agent. I will tell you later on why we use this reducing agent. We also add some polymer, which is a capping agent. And the reason we add a capping agent is that basically when the nanoparticles are formed, we don't want these nanoparticles to mix with each other. And the reducing agent basically reduces the metal salt into pure metallic ions, right? So we take this, we mix it into a beaker, and then we do this, mix it with solvent, and we do the heating process. And then you start to see that small, several metal nuclei start to be built, and then they grow to the right size. And what you will notice, this red boundary outside these nanoparticles, that's the capping agent. That's the polymer. We also call them as ligands, which are formed. These are polymers which make sure that these nanoparticles do not mix with each other or do not merge this. So otherwise they will form big lumps, and then you cannot let them pass through the fine nozzles of the printer, so they will get stuck. So that's why we do this. So then you do some more heatings and centrifuge steps and all that, and eventually your ink is made with the right viscosity, right surface tension, and all that is suitable to your printer. In this case, we made it through a silver nano particle-based ink, a metallic ink. Also, there are a number of printers. I'm going to show you one like a printer example for Dymatics Fuji film printer, which is based on piezo material. So you all know piezo materials. When you apply a bias to a piezo material, it changes its shape. And if you take a vibrating plate, and if you put that vibrating plate next to this piezo material, and when you apply a voltage pulse, you can actually bend this. Now, if this sits on a reservoir with the ink and a small nozzle, whenever you apply a voltage wave, it will enable a drop coming out of it. And if you have multiple of those nozzles, they will all be printing simultaneously, and you on your host substrate, and you will be able to create those continuous traces. Now, the advantage of this is that with the voltage waveforms, you could precisely control every nozzle and every reservoir. So you can make your own waveform that what you want from each reservoir, and that's a very important step for a piezo-based inkjet printer. Now, similarly to the inkjet printers, there's also screen printer. Now, a screen printer is much faster. You're seeing this screen printer video in my lab, where with one of my postdocs, and you could see this just one pass. It passes the ink, one pass, and here you go. A big A4 or A3 paper size designs are ready, right? And basically, the difference between inkjet and screen is that screen you need a screen here because your pattern is here, and it passes the squeegee passes through and delivers the ink to the host substrate, and it goes in the form of your pattern or layout, right? So screen printer is much faster, but the resolution of inkjet printer is much better. So they both are useful in one or the other way. Now remember these red polymers or ligands, right? And these polymers or ligands basically are there when you have printed it. So they are in a solvent and they go to the substrate. So far you do not have continuous traces because these nanoparticles have not mixed with each other. So you need to get rid of not only those ligands, but also these nanoparticles, like the solvent. So what you do, typically what people do is that they dry it in an oven, and so the solvent evaporates, and also these ligands melt, right? So when these ligands melt and the solvents evaporate, then you have these nanoparticles mixed with each other, and then they form these continuous traces. Eventually, this sintering mechanism could be actually linked with the this sintering mechanism could be linked with the printer, so that as you are printing, the things here in this case, this is doing flash sintering, and you could see how roll to roll you could print in a very nice way. There's a roll to roll printer I was been talking about. This here, so you can see roll to roll printers and printing happening, and then sintering happening at the same time. So that's how you then get conductive patterns. Okay, so are you guys still with me? Because I cannot see you guys, so somebody has to say after every 10 slides that we are here.
Yes.
I cannot see you. Okay, so look, with this kind of small tutorial about printing, what can you do? You know, when we started doing, I think 8-9 years ago in my lab, we said, okay, we got at that point, we could not make our own ink. So we got like a commercial ink. Very few inks were available at that point. So it's a commercial silver ink. And we printed it on a photo paper, like a normal paper. And we did, this is a multi-band antenna design. You could see these different sections. And when we were sintering it, we realized that whatever shape you are sintering it, this guy holds its shape, and we did not understand at that point of time. But then we later on realized that this paper has a polymer inside as well, and that polymer gets hardened when we heat it. So, but that's fine because sometimes you need to have this shape permanently. Like if you are attaching to a human arm or if you are attaching to a pole, this is fine. But then we found other papers like tungsten paper which did not have that polymer, and that did not get flexed permanently, and it was you are able to flex it whenever you want in all directions. And this is the same multi-band antenna which you are showing and printed and you tested on it. So beauty of these antennas is that you print it in like 10 minutes and then you use it and you throw it in a dustbin, whenever you want, because you can print 10 more. They're so low cost. But their performance is exactly similar to your PCB based or copper based antennas. They're very similar performance. All of this is published work, and you guys can go and check the performance. I will not have time to show all the performances, but we printed on paper. We printed on the leather. This is a dual band antenna designed for a shoe radar. So it's on leather. And basically one of my students designed a radar on a shoe. So we printed these. This is printing on Kapton, like flexible plastics. And we also printed on t-shirts, normal t-shirts. And this is, I hope in the next slide, I will be able to show you this system of tracking.
we showed you some antenna work. There's a lot of antenna work which we have done based on the printing. I'm going to show you some systems. Here we have designed a system to be able to find or track a lost small child or a pet, and the way we do it is this way. The system is like that. The good thing about our system is that it works both outdoors and indoors, unlike most of the tracking systems which are only GPS based and they work only outdoors. So our outdoor version is the same. Like we have a GPS module which takes the coordinates and it sends out through like you send a message or GPRS. It sends to our server, and the server then displays to any internet-enabled device like your mobile phone or that. You could real-time see the person. This is pretty standard. But then we also, for indoors, whenever you go and inside a building, the GPS signals are lost, right? So you cannot track. So we started tracking based on Wi-Fi. And then we get the coordinates through Wi-Fi. We send the data through Wi-Fi to the central server, and then it enables. So we can track basically both outdoors and indoors. You could see here, this is a field test in KAUST in my university. You could see the green one is the tag which my student is wearing, and he goes inside the building, it's still tracking, as compared to the red tag, which is only GPS based, a commercial tag which only works outdoors. So we patented this technology, and so we can do both outdoor and indoor kind of tracking. And this was done through printing on paper. So you could see that not only the 3 antennas which we have done, which is for GPS or GSM and Wi-Fi, 3 antennas which we have here on one layer, we also have a complete PCB which is printed. And I call it a PCP because it's a printed circuit paper. And then we mount the components through epoxies. And there's the same and all those, and there's thin lithium polymer battery, all stacked in and packaged. And it works well. We have a complete graphical user interface where you put your user name and password, and then you start tracking the kids or the pets, whatever you want, outdoor and indoors. This actually is good with good resolution, like 4 to 5 meters, within the 4 to 5 meters of range. And actually the student who's working on this has started a company, so he's trying to commercialize this, and this has evolved quite a bit since then. Now, when we were doing this, I thought, we are doing it on paper. Can we print it directly on textile? So we took a normal T-shirt, and this is an SEM image of that polyester/cotton T-shirt. And see, there are a lot of holes in this. So when we tried to print directly on it, the ink would just pass through the hole, so we could not print. So we realized that we need another layer of printing. So we created a dielectric ink, just thick ink. This yellowish color underneath is the T-shirt material, and then this thick layer you see is a dielectric layer or insulator layer which we printed, and then we printed conductors on top of it. This is just showing that different T-shirt materials we were able to print successfully, and we were able to flex them and stretch them, and it was working. So then I'm going to skip you the complete fabrication details, but then we designed a Wi-Fi based tracking system, right? So this is, you see your traditional PFA antenna which is printed, and then there is the PCB and everything, and the antenna performance simulation measurements are shown on body and everything. And then this is my student who is wearing it, and he's walking around, and we were able to track him. So this is just Wi-Fi based tracking, and the accuracy is of course slightly lower than the GPS. We were able to track around 15 meters of radius, which is, I think, fine if you're trying to find a lost children or pet. So when I was presenting this in one of the conferences, one of the guys asked me, okay, that's very cool. You can print on textiles and T-shirts, but what about when you wash them, right? So I said, that's a good question. Let me go work on it. So we started working on designs and materials which can be stretched as well as could protect the underlying electronics, right? So we had these inks which can be stretched, and then we also had a cover material on top, like printed layer on top. And this is just showing you a basic filter with 2 shorted stubs. So this is filtering around 1.52 gigahertz. a band pass filter, basic band pass filter, just to analyze. And then we printed it on a stretchable T-shirt, like how the athletes have those T-shirts. And so you could see that you could flex it, you could stretch it, and we did printing through two inks. One ink which is non-stretchable. By the way, the difference between the stretchable ink and the non-stretchable ink is that the stretchable ink, in addition to the metallic nanoparticles, it has some kind of polymer which allows stretching. Right? Of course, we lose a little bit on the conductivity, but then it not too much. And then so the other ink which does not have that polymer, so you just have stretching is not good for that ink. So I show the designs for both, like when it is normal and stretched. And typically, the T-shirt, like a athlete's T-shirt or a stretchable T-shirt, human, it stretches by 30% or so, not more. So we were targeting around 30% stretching. And you could see that the ink, which was non-stretchable, as soon as we stretched it, it developed permanent cracks, right? So it would not work. And the stretchable ink, though it developed some cracks, but as soon as we release it, the cracks would fill up, right? And it would be continuous again. So you could see also here in the performance that when you have no stretching and we have stretching, though the performance is deteriorating a little bit because of the cracks, the conductivity goes down, but it is still working with decent performance till 25% of stretching. And then the one which is non-stretchable ink, one time stretch and that's it. It does not work anymore, right? So that was good. And also then because we have a protective layer on top of it, we washed it multiple times. We washed this multiple times, and after every wash, we would measure it. And after multiple washing cycles, we see that the performance is similar. So this means that on a textile or a T-shirt, you could realize this kind of stuff, and then you could wash it as well. Okay, now changing gears, you also, for a practical design, sometimes on a thick substrates, you need vias, right? Vias are, if people do not familiar with vias, are holes which are conductive, right? So if they connect, let's say you want to connect the back side of one substrate to the top, or if you have multi-layer substrates and you need to make connections, that's how you do. So we have this, a normal PMMA substrate is a known micro substrate, 1 millimeter thick. We took it and we said, okay, we will try to create multi-layer process, and we will try to connect one layer to the other. So we create a via. So we create a via, straight via, and then we try to fill it with printing ink, and the ink would not stick to the walls. So the ink would just go to the other side, right? So it was not working. So what we did, we took a laser and we created these kind of steps, right, on one side, and then we inverted it and we created the same steps on the other side. So it looked like something like this with steps on both sides. Then we printed layers, and because of these horizontal sections, the ink would stick there. And then we invert it and then we print it on the other side. So that's how we were able to create these vias with minimum number of layers. These are showing just pictures of these steps, SEM pictures of those steps. And we were able to make very nice vias. And once we made the vias, we characterized them. And we had very decent resistance from a single via 3.7 ohm and 20 vias around 7 ohm for 40 ohms and 3.7 ohm for the 20 vias. And the average resistance was almost 0.2 ohm, which is very good from a conductive ink and the vias created through lasers, right? And once we know how to do these vias, we did a lot of SIW work. This is just showing a microstrip line to substrate integrated waveguide transition. And then based on this, we did a lot of other SIW work as well, which I hope people are familiar with SIW, which is a substrate integrated waveguide, which resembles a rectangular waveguide, but it is in the substrate. So you need a lot of vias on both sides, which are conductive vias, which make the vertical walls here. So this is showing a very decent performance, and people who are interested more on this, they can read this paper where we show more designs of the SIW. So that's then. We thought of doing a multi-layer process, right? Because the multi-layer process, you could do ground plane, you could do a dielectric, and you could do another signal layer or antenna layer. So because, we want to fully print, not only, so previously I just showed you conductive metal printing, but you want to fully print. So that's why we created this process where we had a dielectric layer, and then we have a metallic layer, and then we have dielectric layer, then we have metallic layer. So we created multi-layer process, And then in order to connect these, we did a very interesting kind of via. We call it a dissolving type of via, which means when you print these layers, PVP layers, which are the dielectric layers, we do not heat them. When you do not heat them, they're still wet, and we print metal where we want the via. So let's say we print metal here. The metallic ink basically goes through the wet PVP because it's wet. It goes through all the way and reaches the other side. As soon as it reaches the other side, we heat it and this solidifies and more ink cannot seep through. So we call this dissolving type of via. It was very, very nice, but it only works for thin layers, as you could see, because it would not dissolve through like a 1 millimeter thick substrate. So for thin layers, it is fine. And this is just showing the vias, with dissolving type vias we made successfully. We made a lot of inductors, capacitors, like multi-layer inductors, capacitors in this process, and we showed these in this paper. Now, we are pretty experienced now, in this field, and we do sintering from multiple methods. We make our own inks, and you could see here that we have a process. We showed for the first time in the world the 3D printed combination with 2D printing, and we actually hacked the ink of the 3D printer and put it into a 2D printer, and we can print thin layers as well. So it is a multi-layer process, again, dielectric metal, dielectric metal, and we can do sintering with all kind of flash, UV curing, and all those processes. And we showed for the first time these fully printed gigahertz components and filters. So this is just showing the performance of this filter, which is working very well, as you could see in gigahertz domains. They are all low cost, fully printed components. We also did a lot of 3D printing in the designs. Again, there's not much time, but you could see that this is a honeycomb substrate with a circular patch antenna, and there's a ground plane at the back, right? This honeycomb substrate, if you want to do it in a traditional manufacturing, it will probably take you a day with the milling and the lathe and all those workshops like machines. Here, we were able to do it in an hour or so. These are concentric rings, if you can see. These are concentric rings. The advantage of this kind of substrate is that you remove a lot of substrate, so you remove a lot of dielectric loss. Also, you make it very lightweight. Right? So make it lightweight. So if the solid substrate was 35 grams, you could make it like really 5 grams. This is very important for space and space applications and like air defense and all that applications. So this is actually triggered this kind of work triggered actually our collaboration with NASA JPL Jet Propulsion Lab, because they are really looking into lightweight components. Again, waveguides, slot antenna array, waveguide based and 3D printed. We printed helical antennas, we printed lens with helical antennas. All of this again is published work, and you guys can look into more details and to this. So there are a lot of 3D printed work as well we have done on the antennas. Now, I'm going to talk about some specialized inks now, right? Functional inks. And again, these are not commercially available. So we make our own inks. We learned how to make our own inks in my lab. And trust me, it was not easy. I'm not a materials guy. And I'm like a CMOS RFIC designer or antenna designer, you can call it. But I realized that in this field, if I have to compete, we have to come up with inks, because there are not many commercial inks, and we need to make new inks. So we did a number of functional inks. So for example, here I'm showing you a magnetic ink. So we make from magnetic, like iron oxide, particles. We made nanoparticles, and then we mixed it with SU8, and then we made our ink. And now this ink we can actually print full substrates, right? So full magnetic substrates. And if you go buy a magnetic substrate, like a good magnetic substrate, like a ferrite or something for microwave applications, for high frequency applications, they're very expensive, hundreds of dollars, right? So here we can just print a substrate, the black one is shown here, and through our ink, and then you could print your inkjet print or whatever your metallic ink on top of that. And we characterized it. It has a decent magnetic properties, magnetic saturation of 1500. This could be improved, because the typical ferrites could have more than that, 3000 all that. But this has decent performance still, right? Because we have mixed SU8, so that's why we lose a little bit on the magnetization. And here we do the microwave characterization by like ring resonators, and we see that the permittivity is around 13 or 14, which makes sense because this is ceramic, right? So the permittivity is typically higher. Now, once we have these substrates and we can print matter on it, what we do, what we like to do, we do antennas, right? So we do an antenna. This is showing a circular antenna, a circular patch antenna. On this brown or dark black or dark brown or black is the completely printed magnetic substrate, and on top of that we printed the metal. It's a fully printed on magnetic substrate. Now what happens is that when you apply a DC magnetic field to these substrates, its permeability changes, or more precisely, its permeability tensor changes. When the permeability changes, the resonant frequency of the component changes. Or radiation, you can also change radiation patterns. You could create phase shifters. We have done phase shifters. We have done phased arrays and all that. Here we're showing a very interesting result where we see that there's a linearly polarized antenna which becomes a circularly polarized antenna. And when you start applying the magnetization, you see as you apply magnetization, and there are two poles which are moving in different directions. So there's a left hand circularly polarized, and then of course there's a right hand circularly polarized, and both these polarizations are after every bias they're working at different frequencies, right? So you could really reconfigure this, and this is just showing you the Meyer radiation pattern, and this is just showing you the axial ratio is around. Not that great, but around 3 or 4. So it's giving you a CP result. So based on this magnetic ink, now we have recently done. I'm not showing you here, but my student has done a phase shifter, and then we are doing phased arrays. So you could like beam scan just by passing DC current, just by passing DC magnetic field. Through this substrate, you could change the properties, and by the strength of the bias, you could control the properties. Another ink which we have made is very interesting because I was looking at some millimeter wave switches, because when you're doing an array design like a Butler matrix or other kind of the feed networks, you need a lot of switches. And if you're doing designs around 30 or 40 gigahertz, basically these switches cost a lot. So one switch costs approximately, from analog devices I checked, around $30. So, and the other problem is that these switches are so small, you need, when you try to attach them to the RF structure, you need very minute soldering. So there's like a tedious work. So I thought if we can make a printed switch, that will be great, right? We can make a low cost and all that. So with this in idea, we started working with vanadium dioxide, a phase change material. What vanadium dioxide is, that it is kind of a dielectric material when it's at a room temperature, and when you increase the temperature to, let's say in this case 68 degrees centigrade, which is the metal transition temperature, this becomes conductor. This is just showing the crystalline structure changes, so it becomes a conductor. So we thought, okay, this is a good material, so let's try to make again nanoparticles of that, and then we made nanoparticles and we created an ink based on this, and then we tried to print the switches. So here you have these CPW lines with these black ones. The golden ones are the CPW lines and the black ones are the switches, right? So series switches or shunt switches. And then we also try to screen print them and print them, of course, on plastics. And these are very flexible sheets. You could flex them and all that. So we were able to print switches which are flexible and very low cost, just with a drop of ink. No soldering required. No soldering. So wherever you need a switch, you just drop one ink and just dry it. So the good thing is they work for high frequencies, like up to 30 or 40 gigahertz. So here we are applying a bias, and we're seeing that when it is off condition, it is a very high impedance, and it is on, the switch is on, right? So it is giving very low resistance, which is typical behavior of a switch. On-off ratios are around 300. Now recently we have achieved 500. This could be further improved, but because the commercial switches, pin diodes or other switches, they can go in 1,000. So this on-off ratio can be further improved. But imagine those commercial switches are $30 or something, come with solid state and all that technology, and this is just a drop of ink. So I think the performance is acceptable for now, but there could be further improvement. And you also pass current through it. When you pass DC current through it, you could switch it really fast, like 0.4 seconds. 0.4 seconds you could do on and off, on and off and off. So that's very, very good speed of turning on and off. And the RF performance is not too bad as well, right? So you have good isolation, 15 dB is 20. And you have in the one of the scenarios shunt, you have very low loss. In case of series, you have a bit higher loss of around 3 dBs. But in case of this is lower than 1 dB. So your switch can work in shunt or series configuration. So just a printed switch with no soldering, no nothing. And then once we have that, we of course try to do reconfigure. Here you are showing again a PFA, but you know this time we have a, this is completely printed, like you could see this is a printed antenna, but we have also printed a switch right here, right? I hope you guys can see my mouse, right? Can you see my mouse?
Yeah, we can see.
Okay, good. So here you can see the black one is the switch printed, and so this antenna is supposed to work in 2 modes. When the switch is off, this arm is not shorted with the ground. So when it is not shorted, it acts like a T type of antenna, which has a different mode. And when this switch turns on, this arm is shorted, so this becomes a kind of an inverted F-type antenna, PFA antenna, right? So then it moves to a different mode, different frequency, which is shown here. So you can use this printed switch in number of applications. And then we also did, one of my students did the filters, reconfigured filters. You could see that you could reconfigure based on 4 or 5 gigahertz. But we have tested these switches up to, I think, 30 or 40 gigahertz, and they work fine. You know, so very, very good, I think, contribution from that perspective. Then there's a lot of demand now on optically transparent electronics, like which means that there is electronics there, but you cannot see it, especially on the car, the antennas on the car windows, and also like the latest FSS, frequency selective surfaces, or now recently reconfigurable intelligent surface RIS. There's a lot of interest to do these in a transparent way, right? And typically the problem with the transparent materials, there are transparent materials like ATOs and ITOs. That the problem with the transparent materials is if you try to increase their optical transparency, their conductivity goes down. So they become bad metals, right? And if you try to make their conductivity higher, like try to make them good metals, they become opaque, like their transparency goes down. So this is a typical known problem in this field. So what we did, we said, okay, we need to tackle this problem because we want higher conductivity, but at the same time, we want transparency as well, right? So we started working with silver, we said we will do silver nanowires. Why silver nanowires? Because silver nanowires are long and narrow and thin. So they're inherently transparent because there are spaces between nanowires, and also they are long and so they're mechanically flexible. So we took a silver nitrate salt, again, you know, the salt, and we mixed with the right solvent and the capping agents, and we made our own nanowires. The length is around 30 micron, 30 to 40 microns. The diameter is around 9 to 20 nanometers, right? So see how thin they are. So 9 to 10 nanometers, and so we made our ink of silver nanowires, and then we started doing designs. But one more thing which we did was that we did a mechanism which is called flash sintering. What we did, that we welded, these are showing the very nice images, you know, SCM images, which are showing different nanowires, and we did flash sintering, or in other words, we kind of welded these nanowires. So we provided multiple paths to the charge carriers to go. This actually increased its conductivity without losing on the transparency. So this is a trick which worked for us. And I think 2 years ago, when was this paper published in Nature Flexible Electronics? 3 years ago, we had the world record of the highest FOM, the highest optical transparency, and the highest conductivity at the same time, simultaneously. I don't know if we still have that record or not, but at that point it was. So we made a very good ink which is optically transparent, and it has good conductivity as well. Then we use it for different designs, and we still use it. Here you see some of the structures which we have shown. They're 80 to 90% optically transparent. You could barely see them. You could see the scene behind. And of course, they are flexible. You could roll these sheets. This is just showing the kind of accuracy we got. Like these are again SEM images, very high resolution SEM images, which is showing the which is showing the nanowires, like how precise we can make these nanowires. Right? We can control their width. We can control their diameters. We can control their gaps. Here is showing image. See how we are able to manage a 50 micron gap between these nanowires. Right? So it was really nice. Then we did a design because there are many places where you, for security purposes or health reasons, you need to control which frequency signals can go in and which frequency signals cannot go in. So we did a design of a frequency selective surface (FSS), which is polarization insensitive, which means that it works with both polarizations, and it will. The design is such that it works with both polarizations. So here we printed this FSS structure. You could see the tree in the background very clearly, right? So it's optically transparent. Performance is very good. And this is, by the way, dual band design. So we did a dual band, dual polarization design, which can work on both the GSM bands, which is 900 megahertz anyway, because we were trying to show that we can block it, right? And you could see that we have different polarizations. We have a kind of same performance for different polarizations. So this was also, I think, TAP paper a couple of years ago. So one of the applications which we showed for this. And then we also did some absorbers. If we, on a periodic structure, if you put a ground plane at the back, this becomes absorber. Absorbers are very important. You use them in anechoic chambers, but you also use them for what? Stealth operations. Stealth operations like dodging your radars, right? So because the microwave absorbs all the radiation. So we did this basic design, and we did it now this on a PDMS substrate, which is like flexible, stretchable, right? And we have a ground plane on the so we printed this design. Again, you can see it's very, very transparent. And we had decent 80 to 90% of absorption in a broad band, like the complete X. I think this was X band, yeah. So complete X band, we had a very good, we have very good absorption, and we bent it for like many cycles, and we was still able to do it absorption. We stretched this as well. This is stretch release cycles, and with stretching and all that, it worked as well. So a lot of designs now. Right now, I'm not showing you here because I cannot show that yet. We have a project from Ericsson Europe on doing these optically transparent RAS structures for 6G, right? So really high frequency and really optically transparent. So this field is picking up actually over and there's also, we've been approached by company to do these antennas on the cars, like cars, windows, windshields, and stuff like that. So it's a nice area. Now again, we like to do a complete microwave substrates and multi-layer, and here we show that you could take basically this is a ABS 3D printed material, right? So we took a 3D printed material and we created a screen printable ink from it. So why? Because the 3D printing can only do thick layers. If you want to do thin substrates, which are flexible, you cannot do with the current 3D printers. So we created with this ABS filament, our own ink, or you could call it a paste, and we created very, very thin dielectrics. You see up to 8 micron. So we created these different thickness substrates, and these are very low loss. This is very low loss at very high frequencies as well. Again, this is published work. Very flexible. You could do whatever you want. One of my students playing with this. And then you can print conductor on it, and we're showing that the current goes past through this substrate very easily. And we showed multi-layer. So this is just showing a parasitic patch array, so it's multi-layer. So we have ground plane, we have this patch, feeding patch, and then we have another superstrate layer kind of, and then we have these patches. So this is parasitically feeding them. So we demonstrated multi-layer antennas are feasible with this kind of technology. How are we doing it with time?
It's fine.
It's fine. Okay.
We are on in time.
Okay.
Because the talk started at 6:30 and it's 7:19 right now here. So around more half an hour, I guess, 20 minutes.
I have 20 minutes. Okay, I'll try to finish in 20 minutes. Okay. Now let me show you some energy harvesting work as well, which we did in the. So the concept which I showed you in the beginning, where antenna on package, right? So we wanted to make a module where the electronics is embedded, and in the package we do our antenna and we harvest energy. So this is a project where we're trying to harvest from ambient electromagnetic energy, and the more bands you harvest, the more energy you get. So we are trying to harvest from 900 megahertz, 1800 megahertz, because there's the most power, RF power is in the GSM bands, right, in the environment. and then also from the 3G band, which is 2.1 gigahertz. So we tried to do this dipole kind of structure, and then we want to do a fractal like dipole. Fractal means it's self-repetitive, and it introduces multiple resonances. So the first iteration of this fractal antenna design gives me two bands, which are not at the right frequencies, by the way. So we do another iteration. So we added, more structures to it on all sides of this cube, which is, by the way, 3D printed as well. And we see that we are getting close to our frequencies, right? And then another iteration, you see the pink one, and we have a third resonance as well. And eventually, you could see that the red one, we have one right at 900 megahertz. We have one at around 1800 megahertz, and then we have one at 2.1. So these three bands which you want to go. So we design a multi-band antenna on package in this. And then this was all done based on current distribution, right? So somebody asked, how did you design it? So we design it based on current distribution. So where we have the maximum current, we use that part, and we try to add a resonance at the right frequency in there. So you look at the currents. You look at the currents at that frequency, for these kind of designs. So we made this antenna very nice, and then of course we printed it on the 3D printed substrate. But because we want to put the electronics inside it, so we did not print a whole cube, but we print it in a way that we can pack it and unpack it. So you could, and we designed nice hinges here, so that they are you just plug in these different parts, and then you assemble them, and it gets assembled, right? And it has decent performance. Its measurements has the same kind of resonances and radiation, and of course it's a kind of a omnidirectional antenna, so it's relatively lower gains. But the interesting thing is we did a rectifier circuit, and we did a triple band matching network, right? So because we have three bands, right, to match. So we did a triple band matching network, and we did the rectifier, which will convert this AC signal to DC, and you could see this is printed as well. So this is very nice. We printed the complete matching and everything as well, and this actually is inside this cube. So you could see that we start collecting, look at the power, we are collecting with an efficiency of approximately 30 to 40% from the environment. This is free energy, right? This is in the environment. We're just collecting it. And then you could see that collecting from all the bands actually helps. You could get up to 500 millivolts. And depending on the load, you could get some microwatts of powers, which is decent enough to power a IoT node, by the way. And then there's paper, not this one. There's another paper where we actually put an IoT node next to this, and we power that up with this ambient harvested energy. So one thing interesting which we found out, that when we were testing this outdoors, we saw suddenly it would increase. Suddenly the collected power increased, and initially we did not understand what's happening, right? So suddenly from 200 millivolts it will go to 500 millivolts. And then we realized that there's a person close to us who's making phone calls, right? So the more activity, mobile phone activity, the more energy you will collect. So then we looked at the day-night cycles, and we saw that when there's more mobile activity, we are collecting more energy. So that was actually interesting. So this work now has expanded as well, and as I said, there are a couple of new papers where we show integration of IoT sensor nodes. Okay, now I'm going to show you some sensor work. Right, in the last 15 minutes or so, I'm going to show you some sensor work, starting with a very unique sensor for the microwave people, because when I came to Saudi coast, I have never worked with the oil industry. Never. I'm a microwave guy. I have nothing to do with the oil industry. But when I came here, Aramco is the biggest oil company. Probably you guys know Aramco just did a big $75 billion agreement with, I guess, Reliance, like Ambani's company in India. So they're investing a lot in that sector as well. So Aramco is one of the biggest oil companies in the world, and of course we always seek funding. So they came to us with the problem that when they get the oil from the wells, there's actually water mixed with it, and there's multiple reasons for that why the water is mixed in that oil, but they did not have any real-time mechanism to measure how much oil is mixed with the water, because for wells they spend millions of dollars to go in, and it's not worthwhile. They spend millions of dollars on a well which has a lot of water coming with the oil, right? So they came with this problem that they want to do real-time monitoring as they are getting oil from the wells. In the pipes, they want to monitor, right? This is the equipment they were using on the top surface, which was very expensive, thousands of dollars. So a simple idea, as a microwave guy, a simple idea came to my head. I said, let me try that. Simple idea is, if you have a resonator, and if you put this resonator on a pipe, and if there's oil and water mixed going in it, the electric fields go from the top to the bottom ground plane, right here. And the electric fields will see a mixture of oil and water. Now, luckily for us, oil has a permittivity of 2 and water has a permittivity of 80, very high. So the electric fields really see two very different mediums. So this means that you could actually distinguish between water and oil in a non-invasive way. So this is a typical lambda by 4T resonator, believe it or not. But we had some problems putting it on a pipe because this is a microstrip line and this is a curved ground plane, right? So we had to do how much distance between them, because the ground should not couple from here. It should go through the pipe. Also, we did not want the 50 ohm microstrip line to change based on the water and oil, because the whole thing is seeing, right? So we had to add an additional ground plane here to isolate the microstrip feed line, but the lambda by 4 resonator would see that. So this simple concept, actually, it worked like a charm. It worked like a charm. We were able to detect even 1% change, 1% water and 99% oil. We were able to see 1% water in that. And this was more than what Aramco wanted. Right? They wanted. So we built them, we printed them, we printed these sensors, they printed these resonators on the pipes, very low cost. And people can read more details on this paper, and there are multiple patents on this. And it worked very well. So then Aramco took these designs to Houston, USA, where they have a big center, and they have these big flow loops which imitate the oil field, right? So there they pass oil and water with pressure and everything, and they tested our sensor over there, which worked very well in my lab because we were doing some testing, but we were doing static. They came back to me and they said, Professor Atif, your sensor works very well sometimes, and other time it does not work. And I said, no, it works all the time. We have tested it, They said, no, when we change the orientation of this, like for example, let's say this resonator is 90 degrees shifted. When they rotate the pipe, it doesn't work. And I said, oh yeah, it will not work, because if you rotate it, the electric fields will see something different, right? They will not go the whole cross section of the pipe. They will see something horizontal mixture. So you cannot rotate it. And they said, no, this is not useful for us because we have hundreds of kilometers of pipelines. We cannot ensure that the orientation is always like this. So this design is not good for us. And because I have taken money from them, so I had to go back and revisit the design. So we came up with another design, which is helical based, right? So here what we did, the T resonator, the lambda, we start to make it like a curved, like helical around the pipe surface. And then we got another ground plane going on the other side. What that does is that with the curve, the electric field starts to rotate as well. So now you start to rotate the pipe, the electric field also rotates, and it will give you ideally the same response. So this new design, then we printed on the pipes, right? It's showing you here. And then this is now being tested in Houston. The red color, which you see, is a mixture of oil and water, which is going through these pipes. And you know what? It worked. Yeah, it worked very well. You see, whatever orientation they would put the pipe, whatever way they move, it would always work. They give the same response, and we were able. So now they were very happy. So then we had to make them field ready and everything. And again, this was then taken to the field. This is just showing now the sensors inside it. This is all the packaging to go in the field and everything. And this is vertical and horizontal sections. And this is now installed in the fields. My PhD student who was working on this project and now graduated, and he started his own company called Fireflow, and he is now selling these to the oil companies. So it's a very good success story. because a problem came to us and we made something which is now useful for the industry. And trust me, this is still printed sensors, very, very low cost sensors. Of course, we are not selling to Aramco at low cost, okay? We'll be making money. So this is an example of sensors for the oil industry. I'm going to show you another IoT example for environmental monitoring. So large area monitoring, let's say you want to monitor large area for forest fires. I come from Canada, and Canada has national parks which are like 400 square kilometers, huge parks. You drive for hours and you're not going to reach the other side. Fire breaks there. You would not know the location until the fire is taken over the whole forest or whole park. Then there's gas leaks from the industry. It can be lethal, right? So you cannot put fixed sensor nodes, expensive sensor nodes everywhere. So our idea here is that there's a disposable sensor node which is printed. You can just throw it. Maybe you could throw it through drones. You could disperse it in large area. These becomes then your ears and noses. They can detect gases. They can detect temperatures, and they have integrated wireless, so they can send that information to a control room, to a server. So this is a design where we are showing, for example, we made a carbon nanotube ink to detect gases, like for example, H2S gas in this case. And we have a P.PSS based ink for temperature sensing. Then we have a air capacitor, which is doing the humidity sensing. And so doing gas sensing, and then we're doing temperature and humidity sensing. And then you see a very interesting antenna design, because if you are throwing a module, you don't know its orientation. You don't know how it will be. So we have designed this antenna, which is all around this package, right? So whatever way you throw, some part of this antenna will be on the top and it will be radiating ideally. And we designed it to have a kind of quasi-isotropic, like all around radiation pattern. Again, we did the PCB, again also printed, so this whole thing was printed, very nice 3D, combination of 3D and inkjet printing. And the results are very good. We can detect temperature, we can detect humidity very well. For all the ranges, we can detect gas really well. Actually, I was astonished that we had very good selectivity to do the gas. And these are just some drops of inks. It's just an electrode printed of inks. It costs cents. These sensors are dirt cheap. You could throw these and then it stops working or dies, throw another one, and then this with the 0 dBm power, this could communicate up to 80 to 90 meters. And then it also has multi-hopping, like one sensor node can talk to the other and to one of the main nodes, which has like GSM capability or something which can send the data. So that's the example of like an IoT sensor node. Then we are also doing recently sensors which can be printed and then can be put on the body, right? So like in the time of COVID, we did this printed temperature sensor again with the vanadium dioxide ink, and we optimized it to work in the human body temperature range, and we printed it, and we did an encapsulation so that it's not gets affected by the sweat or by the moisture, right? Because if you're putting it on human body, your sweat can come in and can foul your measurements. Again, this is printed sensor, and then we also, these are different sensors printed, and these printed sensors are very good sensitivity, a very, very high sensitivity. And we saw that we put it on human arm, and we see that it can work on dry skin, it can work on sweaty skin, and multiple sensors perform the same way. They're printed, and there's no hysteresis. You could turn on and off different temperatures. It's like it's following like different temperatures. And this is just showing different samples, almost producing the same kind of results. And then we also made a complete, like we always do the wireless part. So we designed a wearable antenna, I think wideband to cover the whole BLE band. And then we have this sensor inside the antennas, and then the battery and all the complete PCB, everything inside. So then this keeps on sending the temperature reading through Bluetooth to your phone and all that. This is the printed antenna, and these are the results, and these are just the SAR analysis of that. So we then tested this whole system with a commercial thermometer, and we saw that and we tested it on multiple people, like 10 people actually, and the error was only 0.16 degrees centigrade, which is very good for a very low cost sensor, printed sensor just from the few drops of inks. Again. Again, another project which we did, and I think this is like this last or second last project I'm going to be talking about, is for diabetic patients or chronic wound patients, like people who are obese, who are diabetic, their wounds don't heal in time, and their wounds keep on bleeding, and their wounds develop infection, and if it's on the foot, there's a foot ulcer, very common in diabetic patients. So these patients are admitted in the hospitals and to collect data. When is the bleeding happening? How much is the bleeding? How much pressure is exerted? Is there early signs of infection? They do culture tests. What we want in the IoT domain is that all this data is collected remotely. So people are still at their home and office environment. So we took a normal bandage, normal commercial low-cost disposable bandage, and we created inks like we do, and we printed sensors on it. They do the bleeding patterns and do the pressure exerted on the wound. And also we were able to tell if the wound is becoming bad. Right, and this is all, and then we designed a Bluetooth sticker. So this wireless part is like a Bluetooth sticker which goes on top of this bandage, because we still wanted this to be reusable, right? This sticker, this bandage after the bleeding is still disposable, and then this will send you to the Bluetooth and again to the doctor. This is showing one of the electrodes at the bottom, which is based on a carbon ink. This detects the infection, actually the pH level, and you see there is gaps in it because we want the blood to seep in, so that we can detect the bleeding. And this is the Bluetooth sticker part. This is, of course, you could cover the way as far as I'm going to skip the sensing details. Again, the wireless is integrated sticker. We tested on one of my students. You could see that we can distinguish between blood and sweat very easily. We can tell when bleeding happened. We can give the time instances. It can detect the pressure, how much pressure is exerted in the wound. And it can actually tell when the wound is becoming bad. That's a very good thing, because then you can go to the doctor, and all this with a very low cost commercial bandage, which is disposable. So you use it and you throw it. And the people who are more interested in this, there's a YouTube video. You could go to YouTube and you put smart bandage and you put my name and you will see the video of this. And this is now testing the wireless part on body, and in air you could see that we can communicate up to 60 to 70 meters, which is fine because you just need to send it to your phone, right? And recently what we are doing is we are doing a wireless ECG, printed ECG project for smart health, where we are now printing the ECG electrodes, because what we see that the ECG electrodes are very hard to take off. Some people who have experience of doing ECG, they would say that when you take off that electrode, it's very painful because it pulls the skin. So especially for the infants, So we printed these electrodes with our conductive. We also printed the gel, the glue, the adhesive gel, which actually sticks. We also printed that. So it's completely printed. 3 layers are printed. And this is showing you the printed electrode, which has the gel part, which is the sticky part, is also printed, right? And then very flexible, very nice. And we print multiple electrodes on this. And then, of course, we do all the wireless part. So we have this complete PCB design. We have a very nice antenna design as well. I'm not sure whether it's here or not, but you could see that when we are removing our electrode, there is no skin being pulled. And when this is a commercial electrode, see when you're trying to pull it out, this is pulling your skin. So that's, I think, has a very good value. And then, of course, the wireless is integrated, and the antenna is all around it. So we did a very nice antenna around it. Again, this is Bluetooth. I'm not showing you the antenna here, but these are the acquired ECG signals from this very low-cost wireless ECG signal. And you could see that we tested it with the commercial electrodes, and with the commercial ECG system, and our results are pretty same. So now we are going, in this particular project, we are going to the clinic with the patients. So we're going to be testing like in the coming months on the patients. Okay, with this, I'm going to stop and just a quick summary that printing is a very, very interesting technology. Printed electronics is a very, very interesting development because it can enable you so many new applications which you cannot do it with traditional rigid electronics. Of course, this is low cost, and it works with variable and flexible systems. I showed you many. Some of them I could not show you. However, right now there are not a lot of commercial inks, and there are not a lot of foundries. So that this field is still developing. So we need to work on this. Performance of metallic inks is much improved, but I think we can still improve it, especially for the flexible inks, because the polymer kind of deteriorates its conductivity a bit. And the multi-layer processes are the future, because the PCB, you do PCBs now, they're multi-layer. You could do even like 6 layer, 10 layers, 20 layers, multi-layer PCBs. So that's what I think should be done, more multi-layer. We have done up to 4 layers. We plan to do more. Also, printing of biocompatibility layers is extremely important for wearable applications. I did not talk about that, but we always have a biocompatible layer printed when we are attaching something to the human body. And functional links, of course, I showed you a number of functional links which can do a lot of beautiful sensing for human body or for the environment. Okay, so with this I'm going to stop. This is basically work of my students. I had a number of Indian students or postdocs in my lab. Surajna, she's now a professor in India. She did work in my lab. And Gaurav is here or not? Gaurav's probably here somewhere. He works now for ISRO. And then, Wasim is my printing guy, is also from India. So there's a lot of people from India contribute to my lab, and these are the people and their work which I present. Thank you so much for your attention, and I'll be glad to answer questions now.
Yes, thank you very much. So the forum is open for questions. Are there any questions?
Yes, sir. Sir, Maruti here. One question. You have shown the transparent printing also, material for transparent printing. Is this transparent thing is also disposable, sir?
Yeah. It's a silver nanowires which we make, but you could all make other nanowires as well. They are low cost, they are wires which are dispersed in a solvent, and then I showed you some SEM pictures as well.
Yes.
So it's very low cost and large areas. So the project which we are doing for Ericsson is printing on large areas with this ink.
Okay, sir. Suppose if we want to fabricate in India any commercial or any samples, how we can get it, sir? Suppose if we want to try.
I believe there is good work going on in, I hope I pronounce it right, it's in Bangalore, an institute, IISC, like there's a institute like that. Maybe I'm mispronouncing it, but I think it's Indian Institute of Science or something in Bangalore. There is a printing center there, and they're doing decent work over there. So they are developing inks. They are doing. Actually, I'm just hiring a girl from there, an Indian girl from that institute.
Okay, sir. Yeah, thank you very much.
I can give you, if you send me an email, I can connect you to the girl I'm hiring. IISC, I think it is called in Bangalore.
Understood.
Yes, IISC Bangalore.
Yeah. Okay. Good.
Thank you, sir.
Yes. Any more questions?
Hi, it's Dr. Rashmi over here from IIT Nagpur.
Hi, Rashmi.
Yeah, sir, thank you so much for such a wonderful talk and such a innovative work you have shown to us. Actually, my question is related to whenever we talk about the wearable antenna, we have to more concentrate toward the SAR analysis. Am I correct?
Yes.
So means what method you actually adopted to get the value of SAR within that limit, and which kind of the substrate you are actually selected to get the low SAR value?
So look, SAR, typically people can do SAR through simulations, and people can also do SAR measurements, right? So there are human phantoms where you could do SAR measurements, but in the early stage of design, you could basically do SAR analysis. Any electromagnetic simulator like HFSS, CST, they all have capability of doing SAR. And I showed you in one of the projects the SAR analysis, but whenever we do wearable, it is important. Typically, we are working with low powers, right? So most of our wireless, that's why you see most of my projects is BLE. This is low energy Bluetooth, right? So the reason we use is because the power is very low, right? So we are typically well below the SAR limits. There are two ways you do. There's a SAR specification as well, and there's also specification of temperature rise. There's a degree centigrade or degree Kelvin kind of rise in temperature in your tissues. So there are two standards which you need to see, and we typically look at both of them. So far, to be honest, we did not have trouble with the SAR value. We have always been lower than them. And to tackle a problem where the next part of the question, to tackle a problem where your SAR is more than what you're doing, I don't think so. You could maybe you could use a substrate which is a bit more absorptive, but then, or maybe use maybe a thicker substrate. But the problem with the absorption is then the performance of your antenna will be bad. So this is a trade-off. There's no free lunch in engineering. So you could make less power leaking into your body, but then at the cost of your lower performance. Now, other solution could be, and we have done this in some cases. There's a work which we did for, I did not show here, but for Best Medical Canada, there's a company which does this wireless dosimeter. And they wanted us to put these kind of RFID on the blood bags. So they deal with blood bags. So they wanted to put like RFIDs, blood bags. So we designed and we printed like a complete RFID systems on their blood bags. And the blood was very lossy. And the antennas were like were terrible, So what we did was we put an AMC structure underneath, which is an artificial magnetic conductor. And the artificial magnetic conductor is just a periodic structure with the ground plane, which basically reflects your wave back in phase. People who are more interested, I'm going to be doing more of that in the next talk on Thursday, because we do a lot of on-chip AMC stuff. So you could do like a AMC stuff, which will stop the electromagnetic radiation to go into the human body, and instead will reflect it in phase to your antenna and to actually boost your performance. So these are some of the tricks which you can do to play with the SAR values. I hope I answered your question.
Yeah. Thank you so much, sir. And I hope like by giving the lower voltage, we'll get the SAR analysis up to the level which we want. This could be the one technique, like what you have done.
So BLE, as I said, low energy. So we were using very low powers for wireless, right? So BLE is a standard which, as compared to Zigbee or Wi-Fi or GSM, they all have higher power levels than BLE. So that's why in my lab, you'd see most of the wireless designs I showed, which are wearable, are BLE based. Also, the added advantage is that we can then communicate with the phone, because we just make an app, and because there's Bluetooth in the phone, so we can do that. So using low energy for wearable applications is recommended.
Thank you, sir. Thank you so much.
Yes, any more questions?
Yes, sir. I'm Nitin. So I have one question, sir. Thank you very much for your talk. Question is that how you are powering those sensors you are putting on the pipes?
Oh, okay. So basically the sensors are passive, right? They are just resonators, right? So what happens is that when the mixture of oil and water passes through it, right? Then the electric field see that difference, and the resonant frequency shifts in a passive, like any passive resonator. If you change the dielectric underneath it, its resonant frequency will change. Now this, what you are talking about, the power is for the readout circuit. Circuit, right?
Yes,
so the readout is basically we made a readout of an oscillator circuit. So and this resonator becomes the resonant tank of that oscillator. So the change in frequency actually changes the oscillator performance. And oscillator is very low powered. Again, low power oscillator. And by the way, this is installed in the field, right? So there is no problem in providing them power, right? The more problem of power is in wearable applications or other applications where you need to put small batteries.
Right.
In the field, the oil field, you have connections, and you have to do safety. You have to do safety methods, like we have to make these nuclear like explosive proof housings and all those things. But you could provide power in the field, no problem.
Okay.
So we don't need batteries over there because there is power there, right? But the problem of power comes in when you talk about these IoT sensors on body or in the environment. And we have done both. We have done batteries in them, but you see the RF harvesting project which I showed you. I did not show you the other part. If some people are interested, there's a recent paper where we joined day-night cycle. This is a joint project with my lab and MIT, Professor Michael Strano and MIT, and we did also harvest from the day-night cycle. So thermal. So we added thermal and RF harvesters together. So we call it synergistic multi-source harvester. And these harvesters are enough to power our sensors, right? Depending on the data rate. So then you do not need a battery but you could put it would charge or discharge or a supercapacitor or a battery all the time. So you do not need to worry about changing or charging the batteries.
Okay, sir. Thank you, sir.
And that's the future. I believe that harvesting from the ambient energy, from the ambient sources is the future for IoT sensors.
Yes, sir.
Great. That's great, actually. I guess that's, and I like it was really a great session, actually. Lots of applications and microwaves, like where we have seen, like it's not only of theory, like where we could apply in real life applications, specifically the sensor applications. It was really great, and we really had a great session. Thank you once again for giving this time with us, actually. Within this, like, such a busy schedule, because I know you have been traveling a lot. It was my travel to Milan, and I have been taking rest till now, actually. So I could understand, like, we in your situation where, like, we have been arranging talks and everything.
My pleasure.
So it is really great.
By the way, there's a lot of theory. Of course, I want to show you a lot of stuff, so I cannot, all of these are published papers. So you go, for example, the FSS structure I showed you. There's a lot of theory behind it, which is in the paper. The details are in the paper. There is circuit models, lumped circuit models, and then, so there's a lot of work goes behind it, but I wanted this to be more generic so that you could appreciate the technology more. But people who are interested in more of the designs and the theory, they can find this in the papers.
Yes. Definitely. We'll go through it. Like lots of references also you have shown where I have taken a note of it, and there is always Google Scholar where we could search your name and
right. And my lab's page is impact.cows.edu. So all the papers you'll find there.
Yes. That's really great. So thank you once again, Professor. Hope to see you physically, and hope to, like, whenever you visit India, please ping any one of us. We'll definitely connect, and please visit IIT Kharagpur.
This is definitely on the agenda. I have a lot of friends, Debatosh, and all the other friends in India who keep on, and hopefully we will make one trip there. Okay. Thank you so much.
Yes. Thank you so much once again. So thank you all. Thank you.
Bye-bye.
Thank you.
Bye-bye.
Okay, bye.
Thank you, sir.